Hiya! So in this video, we're going to be looking at, I guess now a third example of expected value, but like in a conditional sense. This one's going to be a little more complicated, so let's have a little bit of fun. So we're going to look at Sn. We're going to let Sn denote the number of successes of n independent trials with probability p of success for each trial. So here, Spidey sense, binomial. Right? Binomial distribution. Independent trials, probability p for each one, and we have n of them. What we're asking is, what is the expected value of Sm given that there's k in n of them? And here we're going to have m be less than or equal to n. So this might seem weird at first, but basically what this is saying is I've done n trials, and I know that k of them were successful. If I now take a subset of that, how many successes should I have, right? So if I have n trials, and like we'll say these ones are the successful ones. There was a gap where there was no successes for a while, and then here at the end there was a lot of successes. And then say I look at m trials, so I look at these m here, and I say, well, okay, how many successes should I have here? And that's basically what I'm asking. What's our expected number of successes in some smaller set? Now the thing is, for this one, we kind of saw the best way to kind of look at this is through indicator functions to see whether one of them are successful or not. And so what we're going to do is we're going to let Sn be equal to just x, the sum of all the xi's. x1 plus x2 all the way up to xn, where xi is a random variable. Why is my pen being so weird? Random variable with a Bernoulli distribution with probability p. Alright, and xi is basically going to tell me whether the ith one was successful or not. So what we have is the law of total probability basically tells me, of total expectation, tells me this I can actually break up into a summation of all of these xi's, right? So this is I is equal to 1 up until m of the expected value of xi given that Sn is equal to k. So we just really need to solve this little smaller part. So hopefully this little smaller part is easier to do. So let's see, E of xi given Sn is equal to k. This we're going to do in the same way. So this, if you recall, the fast way is just to look at the probability. If not, I'll do this slightly slower. I'll say this is equal to I is equal to 0 to 1 of x times the probability that xi is equal to x given that Sn is equal to k. So here you should note that this is equal to just x when it's equal to 0 gives us nothing. So this is just the probability that xi is equal to 1 given that Sn is equal to k. This we can rewrite, right? This is equal to p of xi equals 1 and Sn is equal to k divided by the probability that Sn is equal to k. This bottom one you should know, right? And actually what we're going to do first is we're going to kind of look at this. Yeah, we're going to look at this in two steps. So here I'm going to actually keep this bottom one here. So I'm going to keep this. Let me make sure I have enough room. Yeah, I'm okay. Now let's look at this top thing. And here we have to think about this for a minute. If I know that the ith one is equal to 1, and I know I have k of them that are successful, what is it? So the ith one being 1, this tells me the ith one is successful. They're all independent. So what I can kind of do is I can pull this ith one out. I can say, okay, this is I is equal to 1 times I can look at, well, all the other ones, the n minus 1 other ones. Since I've taken one success out, they're going to be k minus 1 successes. So this is Sn minus 1 is equal to k minus 1. So in other words, what I'm doing here is I take out ith success, leaving k minus 1 successes in n minus 1 trials. And yeah, that's basically what I did. Now these are much more simpler to solve, right? We know all these things. So the probability that xi is equal to 1, well, this is just p. This is our given probability, so it's just p. What is the probability that Sn minus 1 is equal to k minus 1? Well, this again is this is the binomial, right? So we have n minus 1 choose k minus 1 times 1 times p to the k minus 1 times 1 minus p to the n minus 1 minus k minus 1. Okay, all of this we're going to divide by n choose k to the p to the k, 1 minus p to the n minus k. This might look crazy complicated, but we have a salvation. So here, let me kind of bring the n chooses to the front and also write them out properly. So n minus 1 choose k minus 1. This is n minus 1 factorial divided by k minus 1 choose k minus 1 factorial n minus 1. So this is going to be n minus 1 minus k minus 1. But let me look at this for a second. N minus 1 minus k minus 1. This is just n minus 1 minus k plus 1. The minus 1 and the plus 1 go away, and I get n minus k. So here I'm actually just going to rewrite this as n minus k factorial times, I'm going to put the p and the p to the k minus 1 together. So I have p to the k. And then we just saw that this 1 minus p, the n minus 1 minus k minus 1 is just n minus k. So we have n minus k. So here I used this here to get this. And I also did the same thing for this. So these two are coming from that. I still have to divide everything on the bottom. So on the bottom, what do I have? I have n factorial divided by k factorial times n minus k factorial times p to the k times 1 minus p to the n minus k. Whoa! These just cancel. Our p's go away. We don't even care what p is anymore. Bam! It's gone. And then, so what do we have here? We have n minus 1 factorial divided by k minus 1 factorial. And then n minus k factorial. And then here I'll flip it and reverse it. So we have k factorial n minus k factorial over n factorial. Here, these two will cancel. And then this k factorial and the k minus 1 factorial will give me a k on top. And then this n minus 1 factorial and the n factorial will give me an n on the bottom. So this is just equal to k divided by n. Bam! Nice and easy. Or not nice and easy, but like it's a nice formula for this formula. So let's finish our solution. So we have this. So we have E of Sm given as n equals k. This from above, remember this is just, we rewrite this I equals 1 to m, is E of xi given Sn equals k. And this we just solved. This is just k over n. So this is equal to I equals 1 to m of k over n. But there's no I here, so I just sum over this thing. So I'm going to just get m times k over n. And that's it. That's it. Super nice and simple. It doesn't even rely on the probability that any of the trials happen or not. So it's pretty nice. Anyway, That's it for this video. Uh, in the next video, as you probably are noticing, we're going to look at functions in discrete conditional expectation. So we're going to look at what happens if I put a function. So if this Sm, if I put in a function instead, I put in like g of something, what's going to happen? So we will see that in the next video. So I will see you then. Bye.